So this, if we use LCS x and y, is a function notation. I mean, it could return different longest common subsequences. Okay. So that means that means this function is not well defined. So we are, here we just want to, let you know this function definition we wrote there. Okay, is you can say that's notation abuse. Okay, because this is really not, it shouldn't be considered as a function, but at least it gives you a very intuitive idea, okay, what we are looking for, right? And once you understand, okay, this problem, okay, once you have a better picture of this problem, you could imagine, okay, one of the biggest applications of this LCS problem is in the DNA sequence. Okay. For example, I mean, in the literature or in some reports, you say like, oh, I mean, these two species, they are genetically similar. Like, for example, like 90% of their gene, of these two species gene, are similar. What do you mean? 就是我们讲说，给两个种，比如说我们跟黑猩猩好 ，say, I mean, we human and gorilla. Okay, I mean we are very close, genetically, right? So you see like reports that maybe say like, oh, I mean, human and gorilla, like maybe the gene sequence, the DNA sequence, okay, are very close. So what does that mean? That pretty much means like, because like the DNA is a sequence, right? Okay, so the human's DNA, this sequence, and the gorilla's DNA, that sequence, okay? When we use a certain algorithm to compare them, their subsequences, okay, the common subsequences, I mean the longest one is very, very long. Okay, so this is, as I said, like LCS, like one application of that. Of course, like usually, like there are also some modification of this LCS because, like in DNA's like example, in the example of the DNA, like this problem may need to be modified a little bit. Okay, but just for you to understand, like the computational biology also has many problems involving algorithms. Okay, so how do we solve LCS problem? If you are given two like sequences like this, how do we solve the LCS problem? Okay, if you want to do it, okay, by brute force, okay, okay, we will check every subsequence of X to see if it is also a subsequence of Y. I mean, and then find all the common subsequences, and then return the longest one, right? That's probably like an easy solution. Okay. But how many subsequences can we have when we are given a sequence of length n. Remember, this subsequence, its element does not need to be consecutive, right? 就是这个 subsequence 它可以是，就是它的元素可以隔开来。So having said that, we are actually looking for, for every character in the sequence of X, okay, it could be selected, it could not be selected. So there are two choices, right? Okay. So for example, so if our sequence is of length 2, AB, it could be empty sequence. It could be A, it could be B, it could be AB, right? We have 4 such subsequences out here, right? If we have a sequence of length 3, for example, ABC, so it could be empty sequence. It could be A, it could be B, it could be C, it could be AB, it could be BC, it could be AC, and then it could be ABC. So we have 8 possibilities here, right? So you can tell, okay, if your sequence is of length n, for every element you can choose it to be in the sequence or not to choose it in the sequence. So it's the 2 times 2, 2 times 2 times 2. You have 2 to the power of n possibilities out here. Okay, so those are the sequence. Okay, the number of sequences you need to check from the sequence X. But once you are given a subsequence, checking if this sequence appears in the sequence Y is kind of straightforward, right? You just compare. Okay, compare or if the first character match, then you try to match with the second character and then the third character and so on. Because now you have previously you have a moving target. Now at least the target is fixed, right? Okay, so the design of such algorithm is much easier, but you do need to go through the whole sequence of Y. So that's like that takes like a linear time. Okay, so now consider everything. Okay, together. The worst case running time will be big O n times 2 to the power of n. Okay, you have 2 to the power of n subsequences that come from like sequence X, and for every subsequence, you check if that appeared in sequence Y, which take n linear time. So that's the result. So obviously this is an exponential time. I mean, of course, in this analysis, you can easily tell. Okay, n grows much faster. Okay, when n become larger, like your running time grows much faster because n appeared in the exponential place, right? So you may want to, in this case, n and n, you may want to, identify the subsequences, all the subsequences from the shorter sequence of x and y. Okay, in other words, if x and y, say x is shorter, then you use that to generate all the possible common sequences and then compare with y. Okay, if it's opposite, then of course you generate all the some common sequences from Y and compare with like sequence X. Okay, so basically like this is the brute force approach, and it is not a good idea. Okay, because it performs poorly because it's the worst case running time is exponential. We don't like that. Actually, okay, by the way, in algorithm, okay, if your algorithm is like n to the power q, we already consider that as an expensive algorithm. Okay, we usually prefer linear or sublinear. What do we mean by sublinear? Something like n log n. Okay, this type of stuff. Okay, is preferred. Okay, in the algorithm, area. If your algorithm degree is higher than sublinear, for example, n squared, n cubed, okay, usually the researcher in algorithm, okay, area will try to find ways to optimize that. Not to mention exponential complexity. That's just unacceptable. So, we want to design a better algorithm. Okay. So, before that, let's try to simplify the problem a little bit. Okay. Previously, we want to output the V, well, I should use V, one longest common subsequence. Okay, but we could do it the other way. We could look for the length of the longest common subsequence. If you are able to come up with the length of longest common subsequence, okay, the problem, well, it may not be any easier, but at least remember like the issue we have. I told you LCS XY is not a function. Okay, because there may be multiple longest common subsequences out there. So this LCS XY is not well defined. Okay, but now, if you try to use LCS XY to define the length of the longest common subsequence, then it will be a well-defined function, right? 就是前面我们讲说 LCS XY 这个不是一个function，因为它没办法 well define，因为两个 sequence X Y 它可能有很多不一样的 LCS， 所以你没办法用这个写成一个 function。但是如果说我们考虑的是 longest common subsequence 的长度，那不管你的 LCS 有多少，它的长度一定是一样，对不对？所以你就可以用 LCS XY 来表示这个长度，那就不是这个定义就 OK 了，对不对？So this is the idea. Okay. So first we try to formalize. Okay. This idea. Okay. So we focus on the length. Okay. We focus on the length, and then and also in here. Okay. We will use another algorithm design principle. Okay, incremental design. Okay, what is incremental design? It's like if you are able to solve this problem, the problem of this size. Now you try to consider the problem with a little bit bigger size. And you try to see if you are able to extend your solution, okay, for a longer problem. Okay, we call that as a incremental design principle. This incremental design principle appear very, very common. For example, okay, just in this class we use it many, many times. For example, like insertion sort is one of such example, right? Okay, we consider we finished the previous common numbers. Now there's a new number, one additional number comes in. We try to find the rightful place for that number. So that's pretty much insertion sort, right? And so insertion sort is all about incremental design. There are other examples out there, okay, that we already covered. But anyway, so we want to use that principle here as well. But before we continue, okay, we want to introduce a notation. Okay, we denote the length of a sequence S as just like absolute value of X, absolute value of S. Okay, this notation is common, especially in like algorithm and computational theory field. Okay， 就在我们在处理文字的时候，这个 S 的这个绝对值啊，我们叫它是 S 的长度这件事情，这个是这样讲，就是很常使用的 notation。Okay, it's just like previously, like you probably didn't, if you never, manipulate like a string. Okay, this is the notation you can understand, and we are going to stick with this notation. Okay, when we introduce the algorithm of CS. So now, okay, comes the incremental design principle. Okay. So the strategy, we consider the prefix of X and Y. 就是 what is prefix? Prefix 就是 X 跟 Y 的前面的部分。For example. Okay. So this is X, right? The prefix of X could be A, could be AB, could be A, B, C, could be A, B, C, B, it could be A, B, C, B, D, it could be A, B, C, B, D, A, it could be A, B, C, B, D, A, B. Okay. Anyway, we start from the starting part of X. So any length starting from the beginning, ending somewhere. Okay, for example, ABC. It is we call it as a prefix of X. Okay, so prefix is not unique for a given sequence. But if I tell you prefix of a certain length, then it is fixed. 就是 prefix 就是字串的前面的部分，那前部分当然可以是就是长度不一样，对不对？ 那我如果跟你讲说，哎，我们 prefix 长度是3，那就是在 x 来讲就是 a b c，对不对？这样讲 ，OK， so hopefully you understand what we are talking about because the discussion of the algorithm lies in the idea of the prefixes. Okay. So the x1 to I is prefix of x. Okay, prefix of x. The length of prefix here is I, right? And here is the prefix of y. The length of this prefix of y is j, right? 对不对？对不对？这个是 x 的 prefix， 长度是 I， 这是 y 的 prefix， 长度是 j， 对不对？好，我们考虑这两个字串 ，we consider these two sequences. Okay, and we want to find the longest common subsequence of these two prefixes. And we define the length of the longest common subsequence, okay, here, to be Cij. So we try to simplify our notation. So Cij means the length of the longest common subsequence of two prefixes, one from x and the prefix length is I, the other from y, the prefix length is j. So we define that as this function, this Cij. This Cij function is well defined. Okay, there is no other, how should I say, like you cannot have like more than one answer to this Cij. Even though your LCS, the longest common subsequence may not be unique, but their length must be the same. Right? So once you define this, then the problem of finding a LCS for the sequence x and y will be, okay, CNN, right? So our eventual goal is to find CNN. Because when we say the prefix of x with length n, well, that's pretty much the sequence x, the whole sequence x. And n is n, if this n represents the length of the prefix y, then again, that pretty much means the whole sequence y is considered. Okay, so CNN is our solution. Okay, if you want to, find the length of the longest common subsequence. So far so good, right? Okay. Oops. So we now have like the definition, everything clear out. So let's take 10 minutes break. When we come back, we will talk about this recursive formula.